In this video, we're going to discuss Chapter 3, Damped Free Vibration of a Single Degree of Freedom System. So far, we've talked about undamped single degree of freedom systems undergoing free vibration. So here we're going to add damping. So we're first going to talk about what is damping and the different forms it can take, and then discuss free vibrations of a damped spring mass system. So first, let's talk about what do we mean by damping and what are the kind of different forms that it can take. So the loss of energy from a vibrating system can have many causes, but this loss is present in all real physical systems. So far, we've only considered undamped systems, but these are idealized systems, and any real system will have some damping present. So the four main causes of damping are Coulomb damping or dry friction damping, fluid damping, which is sometimes called velocity square damping, solid damping, which is sometimes called hysteretic damping, and viscous damping or slow fluid damping. So Coulomb damping is caused by parts moving across one another without lubrication. Basically, a frictional force opposes the motion and is proportional to the normal forces between the surfaces. So we have this frictional force Ff proportional to the normal force N with some coefficient of friction. The friction force is in the opposite direction of motion, but is independent of the velocity, so it's only related to the normal force. The governing equations are linear, but only until the direction changes. So it just has one half cycle of linearity, and then when the direction changes, the force changes, and so the equations become nonlinear when you go for more than half a cycle. Fluid damping is caused by fluid resistance of a medium, so for example, air or water resistance. Basically, a drag force opposes the motion and is proportional to the velocity squared. So we would have some frictional force here that is proportional to velocity squared, where v is the relative velocity, c is the drag coefficient, rho is the fluid density, and a is the projected area of the mass normal to the relative velocity. Hysteretic damping or solid damping is caused by internal friction within a material. So for example, viscoelastic materials. It's proportional to both the velocity and the displacement. The stress strain curve of the material shows this hysteresis when the body undergoes vibrations. And then viscous damping is the most common damping mechanism modeled in vibration analysis. The damping force is proportional to the relative velocity, and it's acting in opposition to the relative motion. So it's used to represent damping where there is fluid film, like between two surfaces, that's well lubricated, fluid film in a journal bearing, fluid flow through a small opening or restriction, fluid past a piston in a cylinder. The governing equation for viscous damping is that the viscous force F is equal to, or the damping force F is equal to C x dot, where C is the damping coefficient and x dot is the relative velocity. The units of C are Newton seconds per meters for SI units. And it's commonly used to model damping even in situations where it is not really applicable. And it's really the only damping model that we will discuss in this lecture series. The reason that we use it, even when it's not the most representative of the damping in the system, is that most engineering systems actually have very little damping, so it is generally a good approximation, and generally it works well, even in cases where the damping mechanism is a little bit different. And the kind of advantage of using this type of damping is that the governing equations are linear, so it's easy to solve. So we're going to use viscous damping in all of our problems. So let's discuss the free vibration of a damped spring mass system. So far we've considered undamped spring mass systems where we just have a mass and a spring. Now we're going to add a damper. And so the way that we draw a damper, because it's a viscous damper, we draw something kind of like a little piston to represent this viscous damper, and then C is the damping coefficient. So this is the simplest possible spring mass damper system. We can draw a free body diagram, mass acceleration diagram. So if down is positive, if the mass is moving down, which is our positive direction. The acceleration is mx double dot, so our ma. And then the restoring force, we have two restoring forces in this case. So the force in the spring, which is kx, and now the force in the damper, which is cx dot. So the force in the damper is proportional to the velocity, so x dot. Now we can write our Newton's laws. So the sum of F is equal to ma, down is positive. We have minus kx minus cx dot is equal to mx double dot, which we can rearrange as shown here. So mx double dot plus cx dot plus kx equals 0 is the standard form of the equation of motion for a single degree of freedom damped spring mass system. So you can see that it's very similar to the undamped case, where we still have the 0 on the right hand side. We just have this additional term representing the damping. So this is the governing equation of our system. It's a linear, second order, ordinary differential equation with constant coefficients. So we can assume a solution of the form x of t is equal to c e to the st. And then we can take the derivative of this. So x dot is equal to cs e to the st. X double dot is equal to cs squared e to the st. And now we can plug these values into our equation 3.1 to get the expression shown here. So again, this was our x double dot, our x dot, and our x. We can cancel out all of these common terms in each of the terms, and we get ms squared plus cs plus k is equal to 0. So this is the characteristic equation that is used to find the values of s. We can solve this for s using the quadratic equation, and we see that s has two roots. So s12 is equal to minus c plus or minus the square root of c squared minus 4mk all over 2m. We can rewrite this just by bringing the 2m into each of the separate terms. So each of these roots, s1 and s2, provides a solution to our equation 3.1. Now the function x of t is a linear combination of these two solutions corresponding to the two roots. So x1 of t is c1 e to the s1t, and x2 of t is c2 e to the s2t. And the total solution is just this linear combination of these two. So where c1 and c2 are arbitrary constants that must be found from the initial conditions. And at this point, they can be complex numbers. Now we can notice that there's a radical term or a square root term in the roots of the characteristic equation. So we have this square root of c over 2m squared minus km term. So we need to take a little bit of time to look at this term. So if the value of the term under the square root is negative, then the term becomes a complex number and the system changes behavior. So the point at which this behavior changes is of particular importance. So basically when that term goes from positive to 0 to negative, the system behavior changes. So we can define a critical damping constant, which we'll call Cc, to be the value that makes that term under the square root identically 0. So the it was c over 2m squared minus k over m equals, when that is identically 0, we say that the amount of damping, the damping coefficient that makes that 0, we're going to call a special term, which is the critical damping constant. So we just add the subscript c. So Cc, the critical damping constant, is equal to 2 times the square root of mk, or 2mp. You can see that we can rearrange this, knowing that p is equal to the square root of k over m. We can equivalently write this as 2mp. Now this is an important definition for the critical damping constant. Now we can define another term called the damping ratio, which we use the Greek letter zeta, as the ratio between the actual damping in the system and this critical damping constant. So zeta is equal to c, which is the actual damping coefficient of the system, divided by the critical damping constant. We remember that c over 2m, or we can know that c over 2m can be rewritten as shown here, which is, so this becomes zeta, And then Cc we said was 2mp. So C over 2m is equal to zeta p. This is just important because this appeared in our previous form of the equation. So the roots of our equation S1, S2 was given as shown here, and now we can use this to rearrange and rewrite this result. So S12 is equal to minus zeta plus or minus the square root of zeta squared minus 1, all multiplied by p. So these are the roots of our equation. So with the roots of the equation in this form, the general response becomes this expression here. So again, the general response was the linear combination of the two roots. We had c e to the s1 pt, or c e to the s1t plus c2 e to the s2t. And so now we're plugging in our s1 and our s2. So this applies as long as zeta is not equal to 1. If there's no damping, so zeta is equal to 0, we can see that this would simplify to the expression here, which is identical to the equation 2.5, which we calculated earlier for undamped systems. So if zeta is equal to 0, we've got no damping in the system, we do recover our undamped expression. So now we have three possible situations that can occur for damped systems. Zeta can be less than 1, which we call an underdamped system. Zeta can be equal to 1, which is a critically damped system. And zeta can be greater than 1, which is an overdamped system. Now, the majority of engineering systems that we will deal with in this course are underdamped, which, as we will see, gives us this oscillatory behavior that we typically see in these vibrating systems. But we will right now consider each case. So first, let's look at the underdamped response. So zeta is less than 1. So if zeta is less than 1, then that means the square root of zeta squared minus 1 is equal to I times the square root of 1 minus zeta squared. So then we can rewrite our expression for the total response of the system as shown here. So this is what we had before, and this is if we know that zeta is less than 1, then we can rewrite it as this here. We can factor out this term e to the minus zeta pt. It appears in both, and we have this response here. So now the term in the brackets is similar to what we arrived at for the undamped response previously. So we have this c e to the I something plus c2 e to the I something with t in the exponent here. So using the same procedure that we used in the undamped situation that we talked about in chapter 2, we could show that this expression can be equivalently written using sine and cosine terms, again using Euler's identity. So now what we've got is that this term that was in the brackets is a sine square root of 1 minus zeta squared pt plus b cosine square root of 1 minus squared pt. Or we can write this as x sine square root of 1 minus zeta squared pt plus some phase angle phi. Again, using exactly the same approaches that we talked about previously in chapter 2. So this equation represents harmonic motion, but now the frequency of the oscillations is actually the square root of 1 minus zeta squared p instead of just p itself. So this is now our frequency of the oscillations. And we call this omega d, which is the damped natural frequency. So again, p is still the natural frequency of our system, but the frequency of the oscillations of a damped system actually occurs at a slightly different frequency, which we call omega d. So now with the harmonic motion component of the equation solved, the full system response can be written as this here. So x of t is equal to this damping term e to the minus zeta pt multiplied by this harmonic motion that occurs at a frequency of 1 minus zeta squared p, which we can equivalently write as this here. So this is the general form for the solution of, or the response of a damped single degree of freedom system undergoing free vibrations. So what does this equation mean? Let's take a look at the different components and understand what this response actually looks like. So we have harmonic motion part of it. The frequency that it occurs at is lower than the undamped case. So it doesn't occur at the natural frequency of the system. It occurs at the damped natural frequency, which is omega d, which is slightly smaller than p. And this harmonic response decays exponentially as energy is dissipated from the system by this damping element. The larger the damping ratio, so the bigger the value of zeta, the lower the frequency and the faster the response will decay. So it's important, again, that we remember that we're talking about the case where zeta is less than 1. So zeta can be anywhere between 0 and 1. And it's typically expressed as a percentage. So you might say that the system has 5% damping or something like that if zeta is equal to 0.05 in the underdamped case. So this is what the response looks like. We have this oscillatory motion. So we have our sine and cosine term here. But you see that we have this kind of exponential decay. So each peak, as we go on in the response, gets smaller and smaller. So it has this kind of exponential decay envelope over this oscillatory motion. The period is, for the damped free vibrations, is related to the damped frequency, which is the square root of 1 minus zeta squared p. So the period is equal to 2 pi over this frequency. Now, if the system has some initial conditions that we can define as an initial position of x naught and initial velocity of v naught, then we can show that the constants in our equation 3.11, our constants a and b can be given as shown here. So which means our total response is given as this expression. So this is the again the standard form of the response of a damped single degree of freedom system undergoing free vibrations. So this is an important expression to note. Now, for underdamped systems, we can use something called the Logarithmic Decrement method to actually calculate or estimate the damping in a real system. So we can do this, use this approach to find the damping ratio by looking at the ratio of the amplitudes between any two successive peaks in the response. So if we have a system that's vibrating and we can somehow track the displacement of the mass over time, we can get a curve that looks like this, and we can just take a look at the peaks in the response and use that to calculate the damping ratio. So for the logarithmic decrement method approach, we can use the idea that the value for the expression of the response is e to the minus zeta pt x sine the frequency square root of 1 minus zeta squared p t plus some phase angle phi. So we can write this logarithmic decrement as we have here. So some peak, and the next peak. So we're looking at the ratio here. So x1 over x2. So x1 is going to be this response at some t1. And then x2 is going to be the same response at t2. So t1 is the time of the peak x1, and t2 is the time of the peak x2, and they're one period apart, so t2 is equal to t1 plus tau. And we know that tau is equal to 2 pi over the frequency. Now, we can note that the sine terms in this expression are actually the same because they're separated by one period. So these can actually cancel out. And we can simplify this expression and rearrange it. So we know that T2 is equal to T1 plus tau. So we can write this as shown here, and we find that x1 over x2 is equal to 1 over e to the minus zeta p tau, where tau is the period. Or x1 over x2 is equal to e to the zeta p tau. And now we can take the natural log of both sides to get this expression. And now we can define some term delta as this natural log of x1 over x2. So the natural log of two successive peaks. The first peak divided by the second peak. So that means our expression can be rearranged as we see here. So zeta is then found as delta over the square root of 2 pi squared plus delta squared. So this is the expression for the logarithmic decrement method. If we can calculate this delta from our x's, then we can calculate the damping ratio in the system. Now, if the damping ratio is very small, then we can actually approximate this in an even simpler way, where zeta is approximately equal to delta over 2 pi. Because if zeta is very small, then this term doesn't really contribute much. We can also, so this was derived for, peak T1 and T2, or X1 and X2, but it can actually, we can actually use any two peaks. So they can be more than one cycle apart. So we could have Xn and Xn plus m at times n and n plus m respectively. So sometimes if the oscillation is going too fast and it's hard to pick off the two peaks in a row, we can take peaks that are separated a little bit farther. So here, the time between the two peaks is then now m tau, so it's going to be m periods long. So our expression that we get becomes this, so the ln of natural logarithm xn over xn plus m is going to be m times 2 pi over the square root of 1 minus zeta squared. And here our delta is going to be this just 1 over m times this natural logarithm. So then this is the definition of delta that's used in our previous equation. So the only difference here is that we've just got the number of cycles that we're considering. So now let's look at the critically damped case where zeta is identically equal to 1. So if zeta is equal to 1, then the square root of zeta squared minus 1 is equal to 0. And the roots of our characteristic equation become minus zeta, which is just equal to minus 1. So the repeated roots both equal to minus 1. So since the roots are repeated, the solution to our governing equation requires a special form. So the solution is x of t is equal to c1 plus c2t e to the minus pt. If the system has initial conditions of x of 0 is equal to x naught and x dot of 0 is equal to v naught, then c1 is equal to x0 and c2 is equal to v naught plus x naught p. So the response becomes this expression here. So x naught plus v naught plus x naught p times t multiplied by e to the minus pt. So you can see that this response is not oscillatory. Due to the presence of this exponential term, the response will eventually decay to 0. But it does not oscillate back and forth. So this is the critically damped case. The last option to consider is the overdamped response. So if zeta is greater than 1. So if zeta is greater than 1, then square root of zeta squared minus 1 is real, positive, and smaller than zeta. So the roots S1 and S2 will be real as well. So the system response will be given as shown here. With their initial conditions, initial position is x naught and initial velocity is v naught, we can find expressions for these values C1 and C2. And so the response is given as shown here, just by plugging these values of C1 and C2 into our equation. So in this case, again, the motion is not oscillatory, and it will eventually decay. The system will approach an equilibrium position. So again, you don't see any sine or cosine terms, so it's not oscillatory, but you have these exponential decay terms. So it will eventually decay to zero, or to equilibrium.